Hi everyone! In today's video, we're going to code a graph attention network using JAX. We will use graph attention layers from jraph library, and we will package those into flax. So let's get started. When I started preparing for this video, I thought it would be easy, because I got an example from Google DeepMind that uses a graph attention network. So what could possibly go wrong? Then I realized that that example uses Haiku, not flax. And if you check Haiku repository on GitHub, you would find a note that says Google DeepMind recommended that new projects adopt flax instead of Haiku. So I thought to myself, why would I post a video about a library that would be discontinued soon? So I decided to convert everything into flax, and once I decided that, I ran into all kinds of problems. But I would like to acknowledge the help of Flax team. They got a very good post that helped me build my notebook. So they caught migrating from Haiku to flax. So they got the code in Haiku and the translation in flax. So that was very useful for me when I start using the flax. Also, this file from jraph GitHub repository, it's called trainflax.py. It used it, unlike other examples that uses Haiku. This particular example uses flax, and it was very useful for me. I actually borrowed some code from here. So here is the code. First, I would like to acknowledge the help of Google DeepMind team that provided this example, introduction to graph neural networks with JAX. But this one, this is the one that uses Haiku. But they provided in the jraph repository, they provided the trainflax.py. These are some references. I'm installing pytorch-geometric and jraph, and I'm importing libraries. Here I'm importing JAX and jraph. Here I'm setting the random seed for reproducibility, and I'm setting the background for the plots to dark background, and I'm initializing an empty list just to save the training, validation, testing accuracy, and at the end I'll plot it using Seaboard library. Here I'm importing Cora dataset from pytorch-geometric, but there is an important note about the split parameter in the pytorch-geometric. So if you go here to split, the type of dataset split, public, full, geometric TCN, or random. The default option is public, but I set it to full. So here is Cora dataset, 2,700 nodes with 1,400 features. These features are bags of words, and there are almost 10,000 edges. These are the labels, and the train mask, the validation mask, and the testing mask. The mask is basically all. It has the length of all nodes, and one if this node belongs to this split. So in the training mask, if this node is set to 1, then it belongs to the training set. If it's set to 0, then it's either validation or testing node. Once I import Cora dataset, I will convert everything into graphs tuple using jraph. So, and I'm using, for all of this, I'm using JAX NumPy. I'm setting the number of nodes to be the first dimension of X, which is actually the number of nodes in pytorch-geometric. I'm setting the number of edges to be the second dimension of edges index, which is this dimension, 10,000. Then I'm setting the senders to be all the nodes in the first dimension of edges index, and the receivers to all the nodes in the second dimension of the edges index. Then I'm converting the training mask, the validation mask, and the test mask. Squeeze here just to remove the redundant dimension. So it will retain 2,000 by 1. So I'm using squeeze. I'm removing this redundant dimension, which is 1, and I'm setting that into one-dimensional vector. I'm also converting the labels to be JAX NumPy, and I'm setting the one-hot label encoding. We will talk about this later, but here, basically what I'm doing, I'm passing to one-hot label, I'm passing the graph labels, and I'm passing the number of classes to be the unique labels in the graph labels. So I'm passing all the 2,700 nodes into one-hot label, and I'm telling one-hot label, please encode those into one-hot encoding. So it will initialize for each node one row vector of length for the number of classes. So in this case, we have 7 classes. It will be 7. And where is the it will sit 1 at the class label. So if this node is class number 3, it will set the third entry of this row to 1. Now let's check if we have the correct data types. Once we imported Cora dataset, everything was in torch tensors, but we don't want that. We want everything into JAX NumPy because we want to work on JAX. So here is the number of nodes, the number of edges, and feature matrix is float32. It's not torch.float32. It is float32, which is the data type that JAX needs, and integer 32 for the senders, receivers, and the labels. And here is how we implement the graph attention network. So these are helper functions. Let's move to the main class, then we will get back to the helper functions. This class is an instance of flax.linen.module. And it takes 3 input parameters. The first layer output, the second layer output, and the final output. Graph attention layers in jraph needs 3 functions: attention query function, attention logit function, and node update function. They provided good explanation for these functions here in the notebook. So these are the main equations from graph attention network paper. HI is the output node features, and it depends on all neighbors of the node I. And the attention function looks into the output features of the node I and into the output features of the node J, and try to quantify some attention between these 2 representations. So the attention query function is W. How are we aggregating the neighbors of the node I? This is the attention query function. And the attention logit function is how we are quantifying the attention between 2 representations, the node I and the node J. So first, we have to take the features, we have to aggregate by somehow the features of all neighbors and try to attain to those nodes. So this is the difference. So this is the difference between attention query function and attention logit function. So at the first layer, we are setting attention query function into make embed function. I think this part needs to be fixed because what this is, it's simply a linear layer using flax. But I can't just pass the linear layer directly into jraph. So they got a note here. Here they say functions must be passed to jraph JNS, but by type does not recognize linear modules as callables. So here we wrap it in a function. So it doesn't recognize flax.linen modules as callables. So I have to wrap it into a function. Borrow this piece of code, and I put it here. I actually wraps a dense layer, which is a linear layer basically from flax.linen, and I pass it to the attention query function. So how are we aggregating the neighbors of the node I? We are applying linear transformation. Then the attention logit function, basically we are concatenating the sender attributes, the receiver attributes, and we're applying a linear layer at the end. At the first graph attention layer, we are not applying node update function, but we are applying that into the second graph attention layer. So our input, which is X, will be passed to the first graph attention layer, then to the second graph attention layer. Here we're setting the optimizer for the network, and we're defining the loss. So we're setting the optimizer to optax.atom with the layering rate for the 0.01, and we are initializing the parameters to a random seed. And we're setting the model state using flax.train state, and we're passing the parameters and optimizer. Then I run into a problem using jax.jit. So if you remember from one of my previous videos using jraph, I just commented jax.jit because it won't accept the mask, the training mask, the validation mask. So the problem turns out to be this error here, non-concrete Boolean index error. And I really thanks Jax team for naming this error, because it cannot be clearer than that. And I don't know how did I miss it the last time, but sometimes you can't get the error even if it's staring at you. It cannot be clearer than that. No non-concrete Boolean indexing, so there's a problem with Boolean indexing. When I checked the Jax error documentation, which is, by the way, very comprehensive and very detailed. They said it's often solved using 3-argument version of where. So what's the problem? The problem, this error occurs when a program attempts to non-concrete Boolean indexes in traced indexing operation. Under JIT compilation, JAX arrays must have static shapes, i.e. shapes that are known at the compile time. So if I'm passing a training mask under jax.jit, jax.jit it doesn't know, because the mask actually removes some indexes from the array. So it doesn't. This is non-static array. It has to be static. It has to be known for jax.jit. So here is a screenshot of the error I'm getting. If I'm using a function called compute loss mask, and I'm only returning and I'm only passing to softmax the nodes that are under the mask, it will throw an error here saying non-concrete Boolean index error. So my ultimate goal is to exclude the validation nodes and the testing nodes from the loss computation, because I want the loss for the training samples only. My solution to this problem, for example, this is the graph train mask. It says true, false, false, true, true. Means this node and these last two nodes are part of the training, and these 2 middle nodes are not part of training. And this is the loss. The loss I'm passing the nodes into the model, and I'm getting a loss at the end. So what I'm trying to do, I'm running the graph train mask and loss into a 3-argument where. This would set these 2 middle nodes into 0. And because I want to compute the mean of the loss for the training samples, I'm passing the sum of where. I'm summing only the loss of the training samples, and I'm summing the train mask. So basically I'm doing this. I'm setting these 2 middle values into 0, and I'm summing these values, and I'm summing the training mask. By summing the training mask, I'm getting the count, which is needed to compute the mean loss. So on the numerator, I'm getting the sum of losses, and in the denominator, I'm getting the count, how many samples. And dividing these, I'll get the average loss. So this is the solution I came up with. I don't know if it's efficient or not, but I think it serves the purpose of finding the loss using a mask. So for compute loss here, I'm passing state, parameters, graph, labels, one-hot labels, because I cannot compute one-hot labels inside jax.jit. I have to compute it earlier. And I'm passing a mask. So the predicted graph, I'm passing the graph into the model, and I'm getting the predicted graph, and I'm calculating the softmax on the nodes. And for the loss, I'm computing the cross entropy between the predictions and the one-hot labels, and I'm using the same logic I explained earlier. I'm summing the losses with the mask using where function, and I'm dividing by the sum of the mask. This would give me the count, and I'll get the average at the end. And the prediction labels, I'm basically taking the maximum along the each row to get the label for each node. And I'm calculating the accuracy between the predicted labels and the labels. And I'm using the same logic again with the accuracy. So first using the logic with compute the loss, then I'm using the logic to compute the accuracy. I'm summing the accuracy with masked entries, then I'm dividing by the sum of the mask. And I'm returning the loss and the accuracy. Here is the train step function, which accepts the state, the graph labels, one-hot labels, and train mask. This is basically a function that calls compute loss. So I have to pass everything before that. And chooses value and grad from flax. So I'm telling flax, this is the function that computes the loss, and it returns one argument, which is the loss, and it has one auxiliary argument, which is the accuracy. Then this function will return the loss and accuracy from the compute loss, and it will return the gradients. Then the gradients will be applied using apply gradients, and at the end it will return the state, loss, accuracy. So in the model for 100 epochs, I'm calling the train step on the train mask. This will go to train step, to the gradient function, to compute loss, then we'll apply the gradients, and it will go back again for the next epoch. Then I'm calling compute loss for the validation mask. This will not go through a graded computation. It only goes to the compute loss using the validation mask, and it will return the loss and accuracy. And I'm printing the step, the training loss, the training accuracy, the validation loss, and the validation accuracy. Here is the result of training. At the end, it got 99% on the training set and 80% on the validation set. Then I'm calling on the testing set, I'm calling compute loss, and I'm only passing the test mask. This will retain the test loss and test accuracy, which is 77%. I'm appending to accuracy list, I'm appending the name of the dataset, the name of the split, and this quantity, the test accuracy, I'm converting that to float, and I'm appending it to the list. Then I'm importing CiteSeer dataset from pytorch-geometric, and I'm converting everything into jax.numpy, and I'm packaging that into a graphs tuple under jraph. It got 57% on the test mask. Here I'm plotting the results. Just a little explanation of what I'm doing here. For the list, using pandas data frame, I'm passing a list, and I'm setting the columns of that list to dataset, split, accuracy. Then I'm using a seaborn bar plot. The dataset will be on the x-axis here. The accuracy is the y-axis, and the split is the color hue parameter. My final remarks on implementing graph attention network on JAX. There are lots of resources on implementing graph neural networks on JAX, whether it's graph attention or graph convolution. There are lots of resources, but the problem is these resources are scattered. Some of these you would find on a notebook under Flax website, and some of these you would find on a notebook under jraph website. Just collecting these resources is a bit hard, and sometimes you would ask whether if this function is compatible with this library or not. So it's not. There's no comprehensive example that just sits the model. Even under jraph library, they are still using Haiku and Flax, and this adds to the confusion of the implementation. But I found jax.jit is a very elegant way to get back to the basics. So I'm computing the average I'm computing the average in a very elementary way. I found it very useful to practice the basics and just to be very careful in the way you are crafting your arrays. You cannot rely anymore on functions like unique, like Boolean indexing. You have to craft your arrays very carefully before passing those into JAX. I didn't test the speed up by JIT compilation, so I'm not sure. But I think it's pretty fast if it gets all of these redundant functionality out and it's only accept static arrays. I think it would be pretty fast on that. That's it, guys, for today's video. If you find this video helpful, please like and subscribe. By the way, you can find a link to the notebook I'm working on in the description below. Thanks for watching. Bye.